Okay, cache replacement policies. Least recently used is a good strategy for cache replacement. And in a set associative cache, it's reasonably cheap to implement. When I say reasonably cheap, I mean let's compare it with what happens with page replacement. Now, if you've studied operating systems, you may know that most systems don't use LRU page replacement because there are just too many pages. But with a set associative cache, we're not able to replace any block in the whole cache. We can only replace the blocks within a set, so we only need to determine which block is the least recently used of the blocks in a set, and that's a much more tractable problem. Now, with the LRU algorithm, we can arrange the lines of that set in an LRU stack, and they're arranged in order of recency of reference so that the most recently referenced is at the top. Here's a trace, actually a famous trace of 5 pages being, or 5 actually in this case 5 lines being accessed that illustrates something known as Biletti's anomaly, but we're not going to be talking about that here. What I want you to notice is that we reference line A. At that point, line A is the most recently used. We then reference line B, and line A is now the second most recently used. When we reference line C, then B and A are less recently used. And when we reference line D, then A drops to the bottom place in the set. We can reference A again, and that merely rearranges the blocks, with A now being the most recently referenced, and D the second most recently referenced, C the third most recently referenced, and B the least recently referenced. So you see what's happened here is that every block in the stack has moved down by 1 except for A, which was raised to the top. Now B is referenced, and again every other block drops down by 1 position. Now we access block E, and E is new to this set, so it's going to replace something. And what is it going to replace? But the least recently used line in the set, which was C. So now E is most recently used, B is next, A is third, and then D is last. Again, all of the blocks drop down by 1 except for the one that was referenced. Now A is referenced, and A was down at position 3, so the block drops down from position 1 to position 2, that's E, and B drops from position 2 to position 3, but A went up to the top, so D is below the block that got raised to the top. It retains its current position. Now, after that, A, B, C, D, and E are referenced, and each time they're referenced, the blocks above them drop down by 1 position. Okay, so that's LRU itself. Now, how are we going to implement LRU in a cache? The book gives 2 examples. First of all, the matrix example, which implements LRU exactly, and second, a pseudo LRU replacement based on a tree that is pretty similar to LRU but doesn't always necessarily replace the same line. So let's look at the matrix situation first. We have block A located in way 0 of the cache, or in a particular line in way 0, and B is located in way 1 of the same set, and C in way 2, and D in way 3. And the blocks are accessed in this order, B, C, A, D. Every time a block is accessed, we start out with everything 0 in the matrix. Each time a block is accessed, the row corresponding to the way is set to all 1s. So when way 1 is accessed, because B is in way 1, then all of the flip-flops across the row are set to 1. This is followed by all of the flip-flops in the column being set to 0. Next, C is accessed. C is in way 2. So all of the bits in the row for way 2 are set to 1. All the bits in the column are set to 0. Then A is referenced, and this is in way 0, so all the bits in the row for way 0 are set to 1, all the bits in the column are set to 0. And then finally we access D. And in this case, all the bits in the way for D are set to 1, and all the bits in the column are set to 0. So now we can read out the blocks in recency of access. The one that's most recently accessed has the highest number in binary, 1110. The one that's second most recently accessed, way 0, which is A, has the second highest binary number, 0110. Third highest is way 2, which was referenced third most recently. That's 0100. And the least recently referenced way 1, which holds block B, has 0000, so it's the lowest numbered. Now let's look at the pseudo LRU tree approach. In this example, we're going to assume that we have a 4-way set associative cache with block A in way 0, B in way 1, and so forth. And our access stream again is going to be BCAD, but then we follow it up with an E, which is going to cause a replacement. We start out with our LRU tree having 0 at all of its bits, and the rule is that when we're accessing a block, if we move left to get to the block, then we set the bit to a 0 that we just traversed, and if we have to move right, then we set the bit to a 1. So when we access B, in order to get to it, we've got to move left and then right, so we set the bit at the top to 0 and the bit over here to 1. Then we access C. In order to get to it, we've got to move right and then left, so we set the top bit to 1 and the bottom bit here to 0. When we access A, we move left and then left to get to A, so we set both of the bits to 0. When we access D, we move right and then right, so we set both of the bits to 1. Now we need to replace a block. This time, since we're replacing, we interpret the bits in the reverse order from which we set them. So a 1 means we go to the left, and a 0 means we go to the right. That gets us to block B, which was indeed the least recently used block. And then when we access E, the block that we just replaced B with, then we have to move left to get to it and then right, so we set the bits to 0 and 1 again. And that's the same way we set the bits when we got to block B in the first access that we did in this example. Now notice that in this case, the access and the replacement was exactly the same in the pseudo LRU tree as it was in the LRU matrix. But that needn't always be the case. However, since this is an LRU approximation most of the time, it will be the way things work out. Now, to finish off, I'd like to ask you how many bits per set are required to keep track of LRU status in both of these implementations.